Good morning, folks. This is Todd Coburn with your Aerospace Strength Series. This video is on load transfer at fasteners. I found many people struggle with this concept, and it's critical for students and industry professionals to understand how the load moves through a part, into the fastener, and out again. Let's take a look at how it works. We can start off by drawing a typical lap joint. So let's just say that we have a plate of some dimension. Let's say that this plate, actually I'll dimension it in a minute. Here's our first little plate, and let's say it has dimensions. Let's say the width of this puppy is dimension B, and the thickness of this puppy is dimension T. Let's say that we have a fastener, which we often show as crosshairs at the center line, but I'll go ahead and draw the fastener location, attaching it to another plate. The other plate sits beneath it, and for starters, we'll just say that it has the same basic properties. It's the same thickness, and so on. And let's say we have this force P acting on this thing that's transferring. So what would happen if we pulled on the upper plate to the left? Then the plate would just slide on the other plate, but the fastener that attaches the two plates keeps that from happening. So how does that load transfer really work? Oh, and we're going to call the diameter of this fastener, we're going to call that, actually let's call it D. Okay? All right. So that's our basic premise. Oh, and let's also say that our edge distance from the center line of the plate, actually let me move that diameter so that doesn't confuse us. We'll draw our diameter D here, and let's make this dimension from the center of the fastener to the edge of the plate. We'll call that E. E is often used as a little variable to indicate edge distance from the center of a fastener to the end of the plate. Okay, we're going to find that there are actually 4 strength checks that we need to make. We're going to have to check the net tension in the plate first. We're going to need to then check shear tear out. We're then going to need to check bearing on the fastener. Actually, let me write that out. And we are then going to check our shear of the fastener. That is actually the order that these checks will need to be made. Let's go ahead, clean this up a little bit, because we're going to see this again, and we're going to be working with this. Let's go ahead and grab our little picture, and let's just copy it over so we can work with it. We'll put a copy of it over here, and we'll put another copy over here, and then let's see, let's make this a little bigger, and let's put a copy over here. Okay, we should be able to show all of our checks now. So let's come back here, and we're going to work on how this load transfers. Let's go ahead and use this color to see when we have this force P, it's going to be moving through the plate like this. The load here is going to have to go around this and back down. It's going to have to bunch up behind the fastener and press on the fastener. This is going to be coming along here, go around the fastener, come around and press on the fastener. Go along here, come around the fastener, and then come around and press on the fastener, and so on. And so on. Can you see that? This gives us a little stress riser. Now, as the load is working its way down the plate, you'll notice we have a number of stress checks that can be made. The first one will be once we get far enough away from the load so the load is distributed uniformly, we could check the stress in the plate. That would be called a gross stress check. Our stress, F, is just going to be P over A. And the area there is just P over B, the width of the plate times the thickness of the plate, right? We could call this the gross area, and we could call that a gross stress check. And the reason we're calling it that, and you see this is the little area we're talking about here. I should have done that with black. Should have used gray. This is the area we're talking about. Now, this is the first check. If this plate is not good for that, the load never gets to the fastener. Okay? But we're often neglecting that check because it's not the critical check. If you follow the line of action down further, you find the next place we're going to need to evaluate is a cross-section right through the fastener itself. And at that point, our area is much less. It's actually the net area. If we take that cross-section, we see our stress check is going to be, we could call this the net stress check. It's P over A again, but this time we're using the net area, and the net area is going to be B minus the diameter of the fastener, we called that a capital D, didn't we, times the thickness of the plate. You'll notice that hole is removing some of the cross-section. If we take a cross-section through there, it removes part of that. If we look at the end of that plate, if we take a cross-section through here, let's do that with let's do this with gray. If we take a cross-section through here and we slap that picture down on our plate, we see the plate is a dimension B wide, and we have this hole D in the middle of it. So the area that load is going through, that net area, is B minus D, all of that times T. And that's what we're using down here. Now, so that means we've actually got two strength checks, but this one is always more critical than the first. Therefore, we'll often neglect this one and only do this net check. What do we check against? Well, this is tension, so we're going to check if we have ultimate loads. We're going to check against FTU, and our margin of safety would just be that allowable FTU divided by F net minus 1. Got it? The margin of safety up for the gross strength check is the same. The only difference is our stress is lower and therefore less critical. If the net strength check fails, the load never loads the fastener at all. It just rips apart right there at the thing. That means our plate would look like this. We've got the plate with the force, and we've got part of that hole, and it rips right here so that we end up with something looking like this. And we go away sad-faced because it broke here in the net section. So this is our net tension check. And actually, if it was compression, the same check would be made. It'd just be compression checking against FCU, which for aerospace materials we usually take as FTU because that's generally conservative. Now our next check is going to be the shear tear out check. Shear tear out. This is analogous to if you have a 3-hole punched paper and you rip it out of your notebook. You're experiencing shear tear out. It ain't a net section check because the whole thing doesn't rip. It's just right there ripping at that little part of the hole. It's not bearing because you're not getting yielding and elongation of the hole, at least not noticeable, not as much as you see that just rips out right from the hole. Okay? We use the edge distance number for that. What we saw, remember, all the load had to come around, and then it has to get behind the part, right? It had to come around behind. It had to come around like this and go this way behind the part. So what we're going to do, what that means, it has to come through this area, going from the center of the hole to the edge of the plate like this, that little area, and on the other side, this little area. Okay? If we look at this longitudinally, we see, let me do that again. We see we have the hole here, and as we're pulling, you'll notice that actually we could see we got two shear planes. If we ignore this piece in the middle, we see that force has to be transferred. That's P over 2, P over 2. And if that is not sufficient, doesn't have a sufficient shear strength, then we're going to end up ripping that middle piece out as this force pushes that out of the material like this. Okay? So what we're looking at is these two little areas, this distance and this distance, which is these two little shaded areas here. The area of each little shaded tear out area is going to be ET, right? So actually our shear tear out check, it's a shear check and we call it tear out, and often we won't use the subscripts, but that's true. It's our force P divided by that area ET, but you'll notice we have two of those, one on every time, one on each side of the fastener. So it's P over 2ET. That is our shear out check. Now, if you have a load P loading up a bunch of fasteners, like 2 or 3 or 4 fasteners, what you should do first is check for what is the shear force per fastener, and then your shear tear out number would be that shear force per fastener divided by 2ET of the fastener, where this is 2, this is the edge distance, and this is T. Since this is a shear check, you're going to check this against FSU. That's the allowable for shear, so your margin of safety will be FSU of the material divided by FS tear out minus 1. Now, one word of caution. This little formula that I'm presenting here is the standard and common way to calculate this in education, and it's actually fine for industry work as well. In fact, it's simple and it's direct, and this is my preferred approach. However, you should be aware that many folks in industry, when they do this, they use a slightly different approach. Instead of using edge distance from here to here, we'll call that E, what they do is they use some angle, and they assume that from some point at some angle, that is the area. So you'll notice it's a little less angle. A lot of times they'll take 45 degrees, and there are other numbers that are used. So a lot of times in industry, they will first calculate what's this distance to here, and they'll take the E minus that little distance, and they'll come up with this. We'll call it E prime. This is another way, a little more conservative way to do it. This is very commonly used in industry, and that's fine too. Yes, it's a little more conservative. Yes, some folks will tell you that that's a better approach, but actually this one is simple, direct, and in my opinion, fine. This one is slightly more conservative and hence also fine. Okay? All right, so that's shear tear out. Now, another common point. In industry, a lot of times shear tear out is not even checked. Why would that be? Well, we're going to do bearing next, but our bearing allowables are developed for edge distance for what we call E over D ratios, or we could use the capital E since that's what we're using, of 2.0 or greater. What happens is when they design these joints, a good design has an edge distance that's twice the diameter of the fastener or more. Actually, usually it's a little more, because what they want to do is you never get that fastener precisely located, and you don't want that to give you a short edge distance. So what they'll do is they say, take whatever the diameter is, they'll multiply by 2, and then they'll go a little further, like a 16th or a 32nd or maybe a little more, so that if their hole isn't perfect, they still have the proper edge distance. If they have to oversize the hole, it still has proper edge distance. If it's misdrilled, they still have proper edge distance. So standard design uses E over D of 2.0. Our bearing allowables, which we're going to cover next, are developed using a E over D ratio of 2.0. And therefore, if your bearing margin is good, your shear tear out margin should be good. Now, you'll also notice that actually, we'll cover that on the next piece. So now that you understand, I'll go ahead and do it here. So what we're finding here is our bearing allowables, FBRU, presented in MMPDS and in our appendix of our handbook, is for E over D ratios of 2.0. For any time our E over D ratio is 2.0 or greater, we're going to use that bearing allowable. If our edge distance is between 1.5 and 2.0, we will use the E over D of 1.5 values, and we will interpolate for the appropriate, so we'll take whatever edge distance we have, we'll interpolate to make sure we get the correct number. And then we'll use that as our bearing allowable. And if that's positive margin of safety, then that also should not require a shear tear out check, because those E over D of 2 values are developed by testing and verified by testing. So are the E over D of 1.5. Therefore, for either of those, if that's the bearing allowable shown in test, that means it didn't fail in shear tear out, and therefore shear tear out is good by comparison. The time we need to do shear tear out checks is whenever our E over D ratio is less than 1.5. If it is, that means we don't have a clear bearing allowable for it, and we need to go ahead and check shear tear out, which is this check I just gave you. Okay, the next check we're going to do is our bearing check. Now we have the fastener or the load behind the fastener, and so now we check bearing. The load has all accumulated back here behind the part, and so it can press on the fastener. Now if we look at this, what happens is we're going to assume that this fastener, let me redraw this. We've got this plate, we've got a load P, and we've got this fastener here. And what we're going to do, and I'm going to draw it slightly thicker here, we're going to assume that that force is reacted. It has to be reacted here at the fastener. We're going to assume it's reacted on a projected area. That little area. The area is actually dt. It's just as if we had actually, instead of having a fastener, if we had a little slot put in there, then that force at this point, P, would be reacted by this force P, which acts on the area of the slot, which is going down into the part like that. So our bearing check is going to be FBRG is equal to that force P divided by that projected area dt. Okay, that's how we do that. The allowables we're going to use this are FBRU, and once again in 3261 we're going to use N7 when we're going to assume that the 2.0 numbers are valid, our E over D of 2.0, and so our margin of safety is just going to be FBRU, that bearing allowable, divided by FBRG, that bearing stress, minus 1. Got it? That's how we check bearing. So we have to check net tension, and if it's good for that, then the load can transfer and try and get behind the fastener, which gives us our shear tear out check. If that's positive margin, that means the load is now in that little area behind the fastener, in the shadow of the fastener. Imagine the shadow of the fastener, and now we have bearing pressing that against the part. We're pretending we have a little flat projected area, and that's our bearing check. If we're good for that, we're now ready to proceed to our shear check, where we're checking shear of the fastener itself. Now, if we look at this, we notice we have this upper plate, which is being pulled this way. We've got this lower plate, which is being pulled this way. We have our fastener, which we often show as just the center line, okay? And so if we have this, that means if we draw our fastener, that means our fastener has a force centered on the upper plate going this way and a force centered on the lower plate going this way. We've already shown that the bearing is good. Now, bearing that we talked about back here, we were talking about checking in the plate itself. Usually the bearing allowables we're using are for the plate material. Actually, we ought to check it for both the plate material and the same bearing stress acting on the fastener itself. Typically, we'll ignore the fastener because the fasteners are often stronger than the plates that they're attaching, and therefore it's often neglected and forgotten about. But if we ever have a fastener, let's say we have a Play-Doh fastener for some reason that's weaker than has a lower bearing allowable in our plates, then we ought to be checking the fastener as well. Once again, industry usually doesn't do that because usually the fasteners are stronger than the plates they attach. So coming back to our shear check, we have these two plates. Now if we look at this, we notice that that these two plates under the action of these loads would come apart. They would slide if this fastener weren't here. So if you imagine cutting them right through this plane, and you take a look, let's look at this fastener in 3D. That means this fastener has a plane here, right here, which looks like this. If we look at that, looking at it like this, that is just the diameter of the fastener. The area of that fastener is just pi d over 2 squared. So the shear check is just a shear stress, which is just that force P divided by pi d over 2 squared. Got it? That's our shear check. We would check that against our shear allowable of the rivet, so our margin of, or our fastener is going to be FSU of the fastener divided by the shear stress of the fastener minus 1. Now, a lot of times when we get fasteners, especially in aerospace, instead of getting the FSU of that, we will get the shear force allowable. And if that's the case, all we need to do is determine what's the shear force on the fastener and write our margin of safety as S allowable divided by S minus 1. So if we think back to what we learned, we have first, we have the we check net tension in the part. Then we check shear tear out in the part. Then we check bearing in the plates and in the fastener. And then we check shear in the fastener. Our net tension should always be checked, although a lot of times if you look at your part, you can go, oh, this is obviously not critical. And if it's not critical, sometimes that check will get left off. Our shear tear out check is one that's often neglected because as long as our bearing, our edge distance is greater than 1.5, we can use the bearing allowables, and that will also validate shear tear out. The only time you need to do shear tear out is if you have an application where your E over D ratio is less than 1.5, or if you have a joint configuration that looks like it's outside of the bearing test data, and then you might want to check that also. Our bearing check almost always gets made, and it's usually made of the plate itself. Although if the fastener is weak, we ought to be checking bearing of the fastener also. That would be that same P over DT, same numbers. The only difference is we now check against the bearing allowable of the fastener material rather than the plate material. And our last check is shear. This is the most common check because anytime we have fasteners, we're going to have this going on. And that is going to be where we're looking at the plane of the interface plane, and it's just P over A, and that's checked against the shear stress allowable of the fastener, or you just check the force of the fastener against the force allowable of the fastener. Okay? You want to make sure you understand the difference between the load transfer at lap and butt joints and other joints, because it's critical. Now we're talking here, we just had one fastener and one force, but if we have multiple fasteners, we have to first check out the force per fastener, and that's what we would use for most of these checks. I recommend, if this all looks so familiar as to be laughable, then you don't need to do any more study on this area. But if any of this is new to you or you don't completely understand it, I recommend you watch this video again and again until you have it. Get a copy of the handbook and read the sections according to that. That would be in the 3261 handbook. That would be section 4.0 to 4.6. All of this assumes that the load goes right through the centroid of the fastener pattern. We will learn how to evaluate loads that are not at the centroid of the fastener pattern, like for an eccentric fastener pattern in our Strength 2 playlist. In lecture, I believe it is 11, is when we start looking at that kind of thing. So make sure you understand this before you go on to the Strength 2 playlist, and then you'll be well armed to deal with a myriad of application analyses in industry. Enjoy.